Welcome to the debate. Today we're focusing on one Ceres, which is the largest object in the main asteroid belt and the only dwarf planet in the inner solar system. Ceres is, at its heart, a protoplanet remnant, but the data from NASA's Dawn mission just completely changed our expectations for a body like this. It established Ceres as a water-rich world with, really complex geology and even cryovolcanism.
Exactly. And that body of evidence that Dawn gave us, it really forces us to look again at how we classify it. I mean, Ceres has this extraordinary amount of water. It could be a quarter of its mass. And its very existence is a challenge to our models of how small bodies form.
So the profound question for us today is, how should the science community categorize its current internal state? Do we see Ceres as an actively evolving ocean world driven by recent deep-sourced geological processes? Or is it better classified as a mostly quiescent, heavily processed protoplanet remnant where any activity we see now is minimal and just waning? So I'll be arguing that Ceres shows definitive, recent signs of long-lived geological activity, all driven by a deep, persistent brine reservoir.
And I come at it from a different angle. While I think we can agree it had a dynamic past, I'm going to argue that Ceres is essentially a body whose major evolution ended a long, long time ago. Any activity we're seeing now is minimal, it's highly localized, and it really just reflects the advanced global freezing stage of a protoplanet whose internal energy is fundamentally limited.
My thesis is that Ceres geology is characterized by dynamic, endogenic activity, and that means processes that come from within, sourced from a long-lived brine reservoir. This qualifies it as an active ocean world, where these subsurface exchanges are still actively shaping the surface. And you can see this immediately if you look at the mountain Haumea Mons. It's arguably the most prominent feature on Ceres, and it really appears to be a cryovolcano. Its significance is its incredible youth. It's estimated to be no older than 240 million years. That's practically yesterday in cosmic time.
240 million years is indeed young for a planetary surface, but its presence isn't proof of current planetary dynamism.
While the very existence of a Haumea Mons suggests its formation was from diaporism, which is this upward movement of less dense material, so in this case, a slurry of brine and silicate particles must have erupted from the top of the mantle. This points to a material exchange between the deep interior and the surface that is, geologically recent, and that requires internal heat and enough liquid to drive large-scale constructive feature building.
Okay, but let's just clarify that the volume of a Haumea Mons is tiny relative to the total surface area of Ceres. And more broadly, the structural data suggests the outermost crust is strong. We're talking maybe 1,000 times stronger than pure water ice, and it's only up to 30% ice by volume. So this strong, mixed crust, it favors the preservation of geological features over time. That suggests rigidity, not, constant, pliable reshaping. My whole thesis is that Ceres is a post-evolutionary body. Its complexity is the result of past intense aqueous alteration and freezing, and what we see now just reflects this advanced freezing stage.
Preservation doesn't rule out intermittent eruption, but the evidence for ongoing liquid processes is even stronger when you look at Achater Crater and those stunning bright spots, the faculae. These are deposits of salts, mostly sodium carbonate and hydrohalite. And the existence of hydrohalite is really the smoking gun here. It's a hydrated mineral that we know dehydrates and just disappears from Ceres's cold, vacuum surface in a matter of, hundreds of years.
That is a powerful constraint, I'll grant you that.
So the discovery of this salt strongly implies that these deposits had to have been in place very recently, certainly within the last 2 million years. This points directly to a continuous, or at least a highly recent, replenishment mechanism from a liquid source below. And what's more, gravity data and structural modeling suggest a deep brine reservoir right below Achater Crater, extending maybe more than 100 kilometers deep. The chemistry points to an alkaline source with a temperature above 245 Kelvin. That supports a long-term liquid environment preserved by internal heat, not a body that is just sealed up and frozen solid.
That's a compelling argument based on short lifespan of hydrohalite. I see that. But have you considered that the dominant surface smoothing mechanism might be passive decay, not sustained resurfacing? I mean, the surprisingly low number of large craters compared to what our bombardment models predict is explained primarily by viscous relaxation. And that's a process where the gravity of Ceres just slowly causes large impact features to flatten out over astronomical timescales. This suggests the main mechanism is passive decay of old features, not the dynamic sculpting of new material through constant cryovolcanism.
I see why you think Ceres is dominated by passive decay, but let me give you a different perspective, using Akator again. The actual physical structure of the crater floor supports current subsurface dynamics. The central dome, Sorelia Fasola, is interpreted by some scientists as being analogous to pingos on Earth.
Ah, pingos. You mean those ice-cored mounds you find in permafrost regions?
Exactly. On Earth, pingos form when underground water gets trapped, freezes, and forces material upwards into a dome. So in the context of Ceres, this morphology suggests that a subterranean brine reservoir is actively freezing and pushing material to the surface in a similar way. This requires current, localized, liquid dynamics and implies that endogenic activity is ongoing, even if it's constrained to this one unique site. That, plus the fact that we have spectroscopic readings that have identified water vapor hazes periodically appearing over Cerealia facula, it just points so strongly to a geologically driven source.
That's an interesting point, though I would frame it very differently. While the recent salt deposits suggest transport of material, the origin of the exceder activity might not be sustained planetary heat. I'm just not convinced that a single impact site, no matter how interesting it is, represents global dynamism. It's much more probable that the massive impact that formed exceder 20 million years ago gave the initial pressure relief, cracking the rigid crust and forming conduits for brines to travel to the surface millions of years later.
So you're suggesting a singular impact-triggered event?
Precisely. The cryovolcanic activity and outgassing we see today is likely driven by the exsolution of gases, so the gases dissolved in the brine coming out of solution as the pressure is relieved, not by sustained radiogenic internal heat. This makes the activity highly episodic and constrained. We have to ask if this localized impact-triggered outgassing really represents the true, sustained planetary dynamism needed to call it a bona fide ocean world, alongside bodies like Europa or Enceladus, which are globally active. And look, I'm just not convinced by the idea of sustained internal heat because Ceres fundamentally lacks the tidal heating mechanism that maintains subsurface oceans on the big outer solar system moons. Those moons are constantly being needed by Jupiter and Saturn, creating massive energy sources. Ceres has nothing like that. When you look at the models trying to explain the long-term preservation of deep brine on Ceres, they all rely on factors like low thermal conductivity because of salt and gas hydrates in the crust.
And how does that affect your classification of it?
It points toward a stagnant, passively maintained relic ocean. It's basically a structure that survived freezing because of the antifreeze properties of salt and the insulating crust, not one that's being actively heated and circulated. And what's more, if you look at the geometry of features like Ahuna Mons, the predicted viscous relaxation suggests that Syrian cryovolcanoes have to be made of far less dense material than the average crust to decay at the observed rates. And that points to specialized, temporary, local melt pockets that are easily dispersed, which just confirms the transient nature of the activity.
I agree that the rigor of intellectual disagreement sharpens our understanding, but while Ceres certainly lacks tidal heating, that doesn't disqualify it. The evidence suggests the long-lived brine exists because Ceres contains enough long-lived radioactive isotopes, things like potassium, thorium, and uranium.
But are those isotopes really sufficient to maintain a liquid layer in a body this small for 4.5 billion years?
They are sufficient to sustain an environment where the differentiation process separated rock and ice, which provided the conditions necessary to preserve liquid water for extended periods in its subsurface, especially when you consider the antifreeze effect of the brine, which is estimated to be around 5% salinity. If that brine existed for millions or even billions of years, even if it's only just now freezing out, it was a dynamic environment for a very long time. And we have to consider the chemical evidence. The presence of organic compounds, long-chain aliphatics have been detected in craters like Ernutet, and a high carbon content overall, with the near surface being something like 20% carbon by mass. It all suggests material cycling from a potentially chemically rich internal environment. That strengthens the argument for Ceres' importance as an active astrobiological target.
It shows deep chemical and hydrological work is or was recently possible, driven by the differentiation that concentrates internal heat and leaches minerals from the silicate core.
That is powerful evidence for past aqueous alteration, I agree. But we're debating the current state. We agree that Ceres had a massive, long-term internal liquid water history. I mean, it's 50% water by volume. The differentiation process, which ended early on, was responsible for all of that chemical work. The rigid crust and the reliance on passive insulation mechanisms, to me, suggest the internal engine stalled out a long time ago. The brine we see now is just the remnant of that past ocean, fighting a losing battle against freezing.
But the evidence for past, large-scale crustal reshaping is substantial, which points to a long-lived, active interior that was dominant for a significant period. The overall size frequency of craters suggests that early cryovolcanism or other endogenic processes erased many features. That's why we see so few large impact basins. The three large shallow basins, the Planitia, with their degraded rims, are very strong candidates for eroded craters, demonstrating that the surface was once highly pliable.
I'll concede that the surface was highly pliable early on, but that pliability is now gone.
The fact that the rocky material is partially differentiated and that its surface is so globally homogeneous and rich in minerals altered by water, specifically carbonates and ammoniated phyllosilicates, it demonstrates a massive long-term internal liquid water history that dramatically altered the entire body. The global distribution of these minerals indicates the material was processed by a substantial amount of liquid water, not just some localized, temporary melt pockets. This deep geological work means we have to account for the duration of that water interaction, which extends far beyond its earliest formation.
I understand the history, but the surface today tells a different story about the balance of forces. The surface is still fundamentally dominated by impact craters. That suggests internal processes have ceased to be the dominant geological influence on a global scale. This is precisely why it is best understood as a protoplanet remnant. Sure, it was once dynamic, but the fact that the largest craters, like the 280-kilometer Kairouan Basin, are still there indicates a modern surface that is far more rigid and is just passively waiting for external impacts rather than being actively sculpted by internal heat. And Ceres's density at 2.16 grams per cubic centimeter, it just confirms its unique classification as a water-rich object that failed to fully form. It stopped short of becoming a terrestrial body. The current, localized features are just echoes of the past, destined to fade away due to viscous relaxation, not the beginning of some new geological chapter.
My position remains firm. Ceres's internal dynamics are highly relevant today. The extreme youth of the salty evaporites and Ocator, confirmed by that fast dehydrating hydrohalite, and the geologically recent cryovolcanic features like Ohuna Mons. They imply a sustained, or at least very recently active, deep brine reservoir that continues to interact with the surface. This active subsurface exchange, driven by radiogenic heat and salt, firmly places Ceres among the most compelling, currently evolving ocean worlds in our solar system. It has the most water in the inner solar system after Earth, and its lack of tidal heating makes it a unique and I'd say robust example of how long liquid water can survive.
And while Ceres clearly harbors water, its current geological dynamism is minimal and localized. It's best characterized as the final episodic release of stored energy from a long-frozen protoplanet remnant. I think the strongest evidence lies in the widespread prevalence of viscous relaxation over sustained cryovolcanism as the main resurfacing mechanism. That confirms that Ceres represents the end state of a body whose major planetary evolution ended early in its history, and it's constrained by a thick, rigid crust. The activity we observe is residual, not representative of a globally dynamic ocean world.
Well, whether Ceres is actively thriving or gently weighing, it remains a critical data point for understanding how ocean worlds might maintain potential habitability without tidal heating. It gives us a completely different set of physics to study regarding subsurface liquid survival.
Absolutely. And the debate over the lifespan and activity of that brine reservoir is what drives our future exploration goals. We need a definitive answer on the temperature, the salinity, and the age of that reservoir. Is it truly preserved and still chemically active, or is it just sealed off and slowly freezing?
Future missions focusing on sample return from sites like a Kuiper crater are, I think, essential to fully characterize that brine environment, including the organic matter and isotopic signatures. Only by studying that material directly can we resolve this ongoing intellectual tension between Ceres's ancient, dynamic origin and its astonishing recent dynamism.